It's been fine. So let me share my another screen. Okay, okay, fine. So last interaction session, we actually discussed about how my amino acids CD spectra looks like. So for that, we need to purpose. We need to think about molecules point group, and then with respect to that point group, if any kind of symmetry operation, let's suppose E or B1 or S, depending on the point group where my symmetry operation is present, in that case, in that symmetry operation, is there any X, Rx or Y, Ry and Z, Rz are simultaneously active or not. If that is active, then there is a chances of the me. Okay, there is a chances of the hello. There is chances of activity of the electrical dipole moment and the magnetic dipole moment, and that becomes the making the my helical dipole moment in the molecular molecular system, and that interact with the my my external light source, which is a polarized light, circularly polarized light. The left hand circularly polarized light, and there is the right hand circularly polarized light. Depending on that, we can say my molecules is CD active or not. So we already discussed, and professor also discussed all those things. And then depending on, so we actually got some result from the how alpha helix and the beta sheets becomes the CD active, and these are the some results we discussed depending on the publications, a few publications. And then there is some data with respect to that, how my microglobin or proteins, all those data are coming, data are showing the how CD active CD spectra can determine if my protein structure is in which structure is dominating on the protein scaffold. Let's suppose we have a myoglobin enzyme where we found that 95% of the 95% is the alpha helix, and then depending on that, all those enzymes, we are getting some different amount of CD activities. Okay, and also we checked with the how depending on the pH, how my protein structure actually changes. Where we found that cytochrome C, in presence of the guanidinium hydrochloride acids, how my protein structure actually changes to its different structure. So we found that there is some concentration where guanidinium hydrochloride concentration is around to 1.75, where midpoint of that sigmoid curve is found, and that is the point of the pH changes around to change my structure of the guanidinium hydrochloride. And for the guanidinium hydrochloride concentration, for the changes of the cytochrome C cytochrome C enzymes. Okay, and then we actually found some result from our group who actually did that. There we have our cobalt histidine moiety, which is a complex which making made of histidine and cobalt, and that actually captured the oxygen and forming a different color, which is also found in the UVs. In the deoxy form, we found there is some DD transition over there around 500 nanometer region, around 525 nanometer region, and then there's some activity, UV's activity around after the 350, below the 350 nanometer region. But whenever you are exposing this complex into the oxygen, aerial oxygen, then you can easily distinguish this molecular complex. The solution of that molecular complex actually changes to a different color. So that color actually found in the UV spectra, where we found that DD transition is near to the same region, but the LMCT, around LMCT, where the oxygen bonds with that cobalt 2 cobalt complex, cobalt complex with the two oxygen bond, that is the peroxo bond we found, and this peroxo has been detected by the Raman spectroscopically. And then this spectra is actually showing some LMCT over there, and there is a very shoulder kind of thing, DD transition. But this DD transition has been recorded very predominantly by the CD spectroscopically, where the deoxyform is DD spectra around 500 nanometer region, which is actually structure is different from the oxyform. In the oxyform, we are getting, this is the oxyform, we are getting the another kind of, this is the oxyform DD transition. Oxyform of cobalt complex. Okay, and then this is the chirality. Actually cobalt is DD, but this DD transition here also in we found in the observance spectroscopically, uh, optical spectra, where the DD transition has been found, but in CD this DD transition is not chiral, but showing some chirality. Because of that, this induced chirality actually go into the cobalt molecular orbitals, cobalt ligand molecular orbital, and that is we found it that deoxyform also CD active. And then in the oxyform, this DD transition also active because of the induced chirality, followed by some LMCT because of the this induced chirality of the histidine molecules. Okay, so this is how, and then we actually introduce some different ligands. First, disacchinite. We actually observed there is some different CD spectra where we cannot find in the UVB spectroscopically. Okay, and then in this class we'll go further for some results. So it is, I will go through in that. So we have some enzyme. There is some enzymes called, let me this. Okay, some enzymes, that is uh, cobalt based some complex, which is actually surrounded by a protein scaffold. That is a cobalt over here. We have sulfur, and cysteine sulfur, and this is the nitrogen, and this sulfur is connected with some amino acids, and this is also connected to this nitrogen on this. And whenever this cobalt complex actually exposed with the influence of oxygen, that will show some interesting result, which is uh, cobalt actually uh, becomes this initially this oxygen sulfur, this sulfur, and that becomes oxidized to this sulfate, and then if you keep this solution for overnight, There is another brown color solution. This is also brown. This is still remain in cobalt 2, and then if you expose this for 24 hours, 24 hours, it slowly goes down into the cobalt 3. This cobalt 3 actually uh, determined by the EPS spectroscopically, sulfur oxygen, and this becomes the cobalt 3, and this is will be the ligand solvent. This is solvent. It's right, solvent or any ligand or L, and this will be the nitrogen. This there it has some different CD activity. So it is a CD spectra. This is how 24 hours. So because of this reaction is very fast. This is the fast reaction, and this is the very slow reaction, because we after getting this brown solution, there is another brown solution. This is also brown color, but we cannot distinguish these two color by the UV spectroscopically. So there is some little bit changes in UV spectroscopy, but whenever if you put this sample into the CD spectra, these two brown solution has a different CD spectrum. So initially, because of this first brown solution is because of the cobalt 2, which is actually this sulfur is getting oxidized. This is cysteine sulfur, and then further exposed to the oxygen, it slowly goes down into the cobalt 3, and this cobalt 3 again it's a brown color solution, and its CD spectra is different than the first brown color solution, that is for the cobalt 2. And this cobalt 2 actually also monitored by the event spectra. In the event spectra there is a cobalt 2, and uh, it is a tetrahedral kind of structure. It is a scorpion kind of structure, and then we have uh, distorted structure, distorted square planar kind of, and then it's going to slowly moves to a square planar structure because of this dd d delocalization of the d electrons, and this pi star orbital of the s double bond O, and is making a flattening of the complex and forming this planar square planar structure, and then planar square planar is not very stable, and then it's oxidized to cobalt 3, and two other ligand from the axial position comes into the together and forming the cobalt 3 octahedral complex. Okay, so this where this picture also a cobalt is not for the DD transition also becomes the chiral, becomes the CD active because of this induced chirality by these enzymes, not enzymes, these amino acids, and which is actually induced into the DD orbital transition for the cobalt complex, and 400 nanometer to 700 nanometer regions the CD activity has been found for this complex. Okay, so we have another example that we had this particular complex. This is the cobalt silane complex. This is the salicylaldehyde, and if you there is salicylaldehyde, this is the salicylaldehyde, and if you treated this amine in presence of the methanol and may reflux it, if you will get the silane ligand, and if you treated this silane ligand in presence of the AR with the cobalt chloride, it's forming this silane cobalt silane complex. With respect to this amine, if you introduce some different amine group, let's this group, Professor Datta's group actually did this experiment. It is already published. It is a well established system. This is R is when benzylamine, and there is the phenylamine, and the tyramine and the tyrosine. In this case, the phenylamine and tyrosine is a chiral ligand. So they introduced some chiral ligand into this cobalt silane complex and try to find out the hydrogen production of that system. So they started with a with that cobalt complexes, with a cobalt what is tyrosine complex, and then they started that with the help of the cyclic voltammogram, that is the CV, and they did the electrochemistry. They found some cobalt 221, cobalt 322, and 221, 221, followed by the for a catalytic peak over around minus 0 point onset around minus 0.85 volt with respect to the SHE. So more interestingly, whenever we are changing the pH, they are getting uh, different electrochemical behavior. So let's suppose from starting from the pH 6 to pH 5 and pH 4, they don't get any catalytic activity over here, but this is remains similar. Whenever which goes down to the another pH 4 to pH 3 to pH 1, they started they find some catalytic activity around here. This is because of the within the this is because of the hydrogen production, and that hydrogen has been found by uh, by the gas chromatography. On the head space of that solution, they collect the gas and purchase in the gas chromatography, and they found the hydrogen. Okay, so this because of this catalytic peak, we are getting the hydrogen. But question is at the pH 4 till pH 4 there is no catalytic activity. Why it is so? So to check that, they actually use some different spectroscopic technique. That is, one is the UV spectroscopy, another is the CD spectra. In the UV spectra, you can check. This is the C4. This is the blue color one. This is the C4 one. You have the LMCT over here, and around the okay, around 800 nanometer region, there is some DD transition. 700 nanometer region, there is some DD transition over there. So they checked, they record the CD spectra of this complex at the LMCT and the pi star transition of the complex, and they found this is the different pH how the LMCT band behaves looks, and the pi star transition actually behaves looks like. And then they record the CD spectra. This the pH 2 to pH 6, starting from the pH 6, they have some CD activity initially at the downwards, followed by upwards, and they again go the pi star into the positive delta epsilon value. And then if you decrease the pH 6 to pH 5 to pH 4, there is no certain changes. Okay, and afterwards at the around pH 3, there are also similar structure of CD in their region of the 450 nanometer to 250 nanometer region. But at pH 2, there is a different CD spectra. This is which is actually exactly different from the at the pH 6 or pH 5 or pH 4, because this phenomena is coming. Why? Now question, why this CD actually changes in the pH. So there is some tyrosine over there, or tyrosine, not the tyrosine. This is the C4, that is C4 is the tyrosine. Okay, this tyrosine has a C double H group. Okay, this double H group. This C double H. This is a pK of. We can draw it over here also. Is a tyrosine. COOH. We have the hydrogen. below the point. And then we have benzene ring, OH. Okay, this this proton has a pK of around 3 to 4. So this C in the at the pH 3 or 2, this tyrosine molecule, the COOH group, has a proton tyrosine group has a some effect of the protonation and deprotonation. At the pH region of 3 to 4. So, for interestingly, they found that whenever the below the pH 4, above the pH 4, this tyrosine molecule, this is the COOH of the tyrosine molecule, actually deprotonated and makes the COO minus. And this CO minus actually coordinate with this cobalt cobalt metal center, and there is they are making a saturation coordination site for the cobalt site. So there is no chances in that case, there is no chances of the proton bind to the cobalt center, and they found there is no catalysis happens. So coordination saturation happens. Saturation at the pH pH below the okay, greater than to 4 pH, deprotonation of the COH, which is indicates the deprotonation of the COH group. Okay, and then whenever it's below the pH 4, this COOH becomes COO protonated, and there is a less chances of the coordination of the this this CO minus ligand, and there is a vacant site over there, the cobalt site. There hydrogen proton can bind at the low valent cobalt center, that is the cobalt 1, and they can produce the hydrogen. So this is the major mechanistic fundamental has been uh, proved by the CD spectroscopy. So we have a CD spectra where we found that at the pH 2 there is a CD defined structure in that the pH 2, and the pH other below pH 3 or 6, below pH 3 or 4, we are getting some deprotonated tyrosine molecule, which is actually coordinated to the cobalt center, and which is not open up to capture the proton and produce the hydrogen. So this is the data we found, followed by some another example is that. So this is the one molecule which is this dye molecule over here. This is the standard exciton molecules we have. We are getting some interesting result of that. Okay, so initially this dye molecule has their own uh, own optical activity because of the this is a chiral amine bond is there. There is some chiral amino acid connected with that, that is phenylalanine over here. This phenylalanine which is connected with that dye molecule, and then depending on that we have they are making a defined exciton aggregations in a defined solution. Initially, this is the solution. This is the black trace. Whatever we are finding, this is the UVB spectra for which is found of the this system, which is found uh, there in presence of the methanol solvent. Now, however, this red color solution, red color curve of that particular that particular molecules in a different methanol water mixture. This is the 70% methanol and 30% water mixture. This is 70% methanol present MUH, and this is 100% OH. 100% MUH. Okay, and they found different UVB spectra. But more interestingly, in the CD spectra, they have different CD for each particular. So that initially the black line, which is actually found, this is CD spectra of CD spectra of this particular system when it aggregate in a very dilute solution, and we don't find any CD activity of where these molecules. When if you increase the concentration of that solution, they started aggregate, and they are forming some aggregation over there and forming a helical kind of structure. If molecule is a becomes helical, they have some chirality. Overall system can have chirality, and they become the CD spectra. And they become the CD active. And where this one found one helical structure actually giving this red color CD activity. Okay, and the other one is actually other one is another isomer of that enantiomer of that helical structure. So 2-degree interaction and the two generated non-degree interaction. This is the standard excitation they are happening, and the generalized excitation happening. So two kind of, one is the right-handed helical structure they are forming, another is the left-handed helical structure they are forming. Just they are forming this uh, left-handed helically my aggregating to each other, and that forming this CD activity, CD spectrum. but but the only this molecule will not show the CD activity in that particular region, which is actually around 300 region to 450 nanometer region. In that region, it's not possible to get the CD activity because of these molecules doesn't have any chiral center for this responsible for the CD activity, because of the this is from starting from this amide group bond to this amide bond. um, okay, yes, this amide bond to this amide bond, there is no chiral center over there. Only chiral center is present over there, but it's not showing the any chirality because of this black line, actually black trace over here, which is actually not active for the CD active CD spectra. But whenever they are increasing the concentration, that means whenever in methanol solution it is not showing, but whenever it becomes the 70 is to 30 uh, methanol water mixture, they are starting aggregating because of the polarity. This is the highly hydrophobic, because of this molecule is highly hydrophobic, highly hydrophobic. Hydrophobic. is highly hydrophobic, and whenever we are actually increasing the polarity of the solution by addition of the water, that they started aggregating to each other and making a helical structure, and which is becomes CD active, and that in the 400 to 500, 450 to 300 nanometer region, they are showing the CD activity. Okay. And but this black solution, whatever we found over here, this is the black solution. In 100% methanol, they are not showing any CD activity. But whenever it's 30% water is added into that methanol solution, it's a 75 to 30 methanol solution, then they started aggregating and forming the CD activity. Similar to the these molecules also, where the R is different over here, X is different over here, here is the X is different over here, and then they are forming also a different CD activity, because the UVB spectra also different over here, and which is actually shifted, this solder is actually shifted towards more red region, and then they are also aggregated and in paints of the 70% of methanol, and also they are so the some CD activity around 450 nanometer to uh, 250 nanometer region. So this is how people can detect that if you change the polarity, these supramolecular systems that can aggregate to a definite structure, that maybe becomes the chiral, and that can give you the idea that my molecules is aggregated or not. If it is aggregated, then it's forming a definite structure, or it maybe becomes CD active, and then we can get some good result from it. Okay, so this is also, and if you increase the hydrophilicity of that solution, hydrophobicity, then this aggregation is not possible in that case. So if there is no hydrophilicity, then we don't get any aggregation. Only we can get the free die molecules, and then will not get any CD activity. Okay. Okay, then there is another interesting result over here. Similarly, this is the another molecule. Can zoom it out, zoom in. Let me zoom this. Okay. Okay. Don't think about the above one. Just go through this part only. This is the chromophore 1, chromophore over here. This is the SOPV, and another is the ROPV. Whenever they are aggregating to each other, let's suppose SOPV. We have an SOPV. They are actually forming a helical structure. M-type helical structure is actually forming, and that M-type helical structure, if you increase the concentration of that, the initially solution is very dilute. If you increase the concentration of that this chromophore, they are started aggregating to each other, because of the there is a strong pi conjugation starting from here. There is a some hydrophilicity one sided, and another sided is the hydrophobicity. In the if you change the polarity of the solution, this hydrophilic side chain, they're supposed to be stay at the outside of the my uh, aggregation structure, that is they can expose to the solvent, because of we are increasing the polarity. But whenever there should be a certain concentration presence in the solution, otherwise it cannot aggregate. And then they increase the polarity. They started, this is the hydrophobic part, they are staying in the in the center, and then Then there, okay, red color is the hydrophilic part, and then hydrophobic part, we are actually in a hydrophilic in a center and the hydrophobic in a outer part. And then their hydrophilic interact with the hydrophilic part, and they stay together. They are making a aggregation and forming a, there is a pi stacking over here. Because of this is a very strong pi conjugation over here, and then they are aggregating to a m type uh, aggregation, and becomes showing the CD activity of the this red color one, which is actually showing a positive CD signal around 425 nanometer, and a two negative around 500 nanometer, as well as the 460 nanometer region. Okay, in the similarly R1 also, R, because of this molecule, this center is the chiral center. Depending on this chiral center, we are actually giving that this is R and S, and this ROPV, they are exactly making a P type of helical structure, which is also a opposite to the M type, and which is also found in the CD spectrum. Okay, so we have our molecules. If you increase the concentration, they are aggregating to each other in that solution, particular solution, and depending on the which polymers is present, they are forming a different kind of aggregation. One is making M type of aggregation, another is making P type of aggregation. Okay, so this M type and P type aggregation, we can easily isolate it by the CT spectroscopically. So this is a very strong evidence that my molecules aggregate to each other, and that can be recorded by the CD spectra. Okay, so we have some interesting result over here. Another fundamental problem. So as we know, some gold plasmonic, everybody may aware about this gold plasmonic nanomaterials can be a very very effective gold nanomaterials, which is generally used huge application. Okay, so in that gold plasmonic nanoparticle, they have some UV band around 500 nanometer region, and followed by a band around 300 280 nanometer, and a strong band around 210 nanometer region. So but this gold nanoparticle, this is forming a only the gold atoms are forming bonding and making a band structure, plasmonic band structure, and making a plasmonic gold nanoparticle. But there should not be any chirality, but they have some chirality, which is actually around 200 nanometer region. Because of that, they have some electronic redistribution into the plasmonic structure, and that is showing the chirality around 200 nanometer region. But the other band, let's suppose we have a band around 500 nanometer region. These are not chiral. If you polarize the gold nanoparticle with the higher energy light, then it becomes the chiral, when the electronic distribution is redistributed to a different band structure, and in that case it becomes a chiral. Right now, if we have lower energies uh, band, let's suppose our band is around 500 nanometer region. This is not chiral in nature. Okay, so which is actually have a evidence about this one is the gold. This is the gold plasmonic. gold plasmonic nanoparticle, which is actually not CD active in the 500 nanometer region. On top of that gold nanoparticle, we are introducing a NPS. Okay, not the NPS is the nanoparticles with flag A3 on protein on peptide chain. Okay, as we know, the all the peptide chain has amide bond. That amide bond actually is over here. This is the N to pi star transition. Sorry, of the amide bond, and then it has no other CD activity over here, no other UVBs. Only we can get over here. We have the N to pi star over here, and the pi to pi star, N to pi star and pi to pi star over here. Star, pi to pi star transition is present over here. Both are combined together. And then if you record it in the CD spectra, here we found that only this flag A3, that is the peptide chain, they are not active in the CD spectra into that 500 nanometer region, but they are active in a 200 nanometer region. When if you combine together into gold nanoparticle, as well as on top of the gold nanoparticle we are actually combining this peptide, and we record the CD spectra, and then we'll get this is the CD activity, this red color CD active combined together. Why this is happening? So now our question will be, this is the initially this gold, this 500 nanometer region should not be active, so was not active, and then when combined together, this 500 nanometer region is responsible because of the golden nanoparticle only. This is not active, CD active only the bare gold nanoplasmonic gold nanoparticle. While we are adding a peptide into the gold nanoparticle, we are getting this 500 nanometer region spectra becomes the CD active and showing a negative value. Definitely, there is some ellipticity. So there is some induced chirality comes into the picture. So this is peptide is for made of huge number of amino acids. They are chiral. They may have some electronic interaction between this. Let's suppose we have some uh, acidic or acidic or basic amino acid into that, depending on the pH of the solution. They may be in a deuterionic form and forming a electronic interaction of of gold nanoparticle and the this ionic 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 what is that ionic peptide chain, partially ionic peptide chain. They have some interaction, electronic interaction. They combine together and forming a induced chirality into the gold nanoprism, and then not the nanoprism, gold nanoplasmonic nanoparticle. And that induced chirality actually responsible for the CD activity into that 500 nanometer region. Okay, so here is the induced chirality is the major responsible for CD activity at 500 nanometer to 600 nanometer region. Okay, more interestingly, we have our peptide has a strong negative ellipticity around 200 nanometer region. But whereas this gold nanoparticle has a only bare gold nanoparticle has a positive ellipticity around in that particular region. If we combine together, they canceling each other. They have one is the negative and another is the positive, and they reduce this intensity of that in the electricity. Okay, so that also making sense that they somehow electronically interacting this gold nanoparticle with the peptide chain. So interaction between gold plasmonic nanoparticle with the peptide chain becomes CD activity of gold plasmonic nanoparticles. Okay, this is the another result. We have some other result also here. This result actually is from a science publications. This is from the science. Which is published in, let me check. This is published in 2021. So the DOI number is you can check this. DOI number is 10.1126. Sorry, 26 science.abd 8576. Okay, this is another phenomena for which they took a gold plasmonic one and they started uh, expose it into the equivalent less amount of high higher higher peptide chain into the onto the nanosurface. They are try to bound the higher peptide chain onto the this nanoparticle surface. When they add a less number of when they have the less number of less amount of the HF into the that surface, they are they are getting a CD spectra for with the day. They are saying finding some decay of the CD spectroscopy. Okay, and then they are added excess amount of IF into that assembled system, nanoparticle hive system, extra free hive into that system. Then again, they found that it's enhancing the city spectra. Now, question is how it's happening, why this is happening. Initially, the less amount of hive is present in attached with that nano with the nano particles, nano plasmonic particles. They're getting some CD. They're finding that some CD when it diminishing into that into the region of the 600 nanometer to 1000 nanometer region, and that the peak shifts towards the more and more what is that negative, more red region. Okay, more red region. But uh, till 10 day 10 they have found a different city spectra of that solution, because of all the higher fringe actually interact bound to onto the surface of the that's nanoparticle. Now they add excess amount of fiber into that system. Okay, they record the city spectra. They found that the excess amount addition, they again forming a different kind of assemble over there, and they enhancing the city spectra because of this higher forming a external assemble outside. This is the external assemble. They are actually attaching, initially they are attaching this hive actually attached to that nanoparticle, but excess amount of this hive actually forming a external aggregation over here, and that actually forming a helical kind of structure over here. Say so that is the form. This kind of aggregation they found into that excess amount of hive was there, when the excess amount of hive was there. And then they found that CD spectra on the time being actually increasing. And then with the conclusion, they found there is some helical kind of structure actually forming over there. And that actually induce this plasmonic one to be increase the CD activity into that system of excess amount of higher is present. And this phenomenon has been recorded and published in Science 2021. This is the DOI number. If you are interested, just look into that publication. They have a huge very good interesting story over there. Okay, so to that we just completed on our CD application. Right now, if you we have some another part of that, that is the Mossbauer spectra. Oh, is supposed to change some slide. Okay, so we have lots of examples in the literature. You can find it. If you have any doubts, then let me know. So nobody actually joining. Someone actually was joined and then left. He or she left. And then if you don't ask any questions, so it's very difficult to follow it up. And whatever I'm getting the problem from the internet or any publications, I'm showing over there. In the exam, you can get a different data, or basically you have to understand if there is some chirality over there. You can get if the light is absorbed in that region for particular chiral part, that can be CD active, and this is that CD activity we can record it in the in instrument, and then we can finally analyze the my systems. Okay, so now we are quickly moved into the another part, which is actually Mossbauer spectroscopy. Mossbauer spectroscopy. Before that, we have to understand why we are talking about the spectroscopy, and when why mass is spectrometry, not the spectroscopy. So, any guess? I don't think so because of the no one is there, so I don't expect any answer. So, mass is called mass spectrometry, but other thing, let's suppose UVs, UV, UV, UVs is called spectroscopy, or IR spectroscopy. Raman spectroscopy. APR spectroscopy. Or NMR spectroscopy. Okay, this is called spectroscopy. This is called spectrometry. Why? The question is why. So, if interestingly, if you look into the some data representation, you can understand. Okay, in the spectroscopy, always you can find one part over here. On axis x, this is the x-axis you are talking about. This is the y-axis we are talking about. In the spectroscopy, we always find some representation of the energy over here. This is the energy representation. Energy representation always be in x-axis, and this one will be some intensity term, which is actually present over here. Let's suppose UVBs. UVBs, this is called, this intensity can be called as a absorbance, or in APR that is called intensity, Raman is called intensity, IR is called transmittance. Transmittance means how much my light actually transmitted from the system, not actually absorbing to the system. So that is one kind of intensity term. Now, in the absorption spectroscopy, this energy term can be written as a, in the UVs, it is called as a wavelength. Wavelength. This is called lambda. In the IR, the y-axis is transmittance, is a one kind of parameter of the intensity, and the x-axis is called wave number, which is nothing but 1 by lambda, which is also a term of the energy. As we know, E equal to h nu. Nu is a c by lambda, is equals hc by lambda, and this this hc nu bar, which is actually 1 by lambda. Nu bar equals to 1 by lambda equals to nu bar. Similarly, in EPS spectroscopy, we have magnetic field at the x-axis, field that is In that case, this magnetic field energy can be written as the G beta is. Is this is the field, right? This is the magnetic field. But in the spectroscopy, let's change the color. In the spectrometry, in the mass, if you look into the mass, you will definitely get in the x-axis, we will get the mass, and there will be intensity term. Okay, so it's showing the mass of the molecule over here and the intensity over here. But the spectroscopy always be energy and the at the x-axis. But in the mass, we are only getting the mass only. This is not connected with the energy term. Okay, so that's why this mass is called mass spectrometry, not the mass spectroscopy. Someone actually saying mass is the mass spectroscopy. Not, never say that. Mass is the mass spectrometry, and spectroscopy always be x-axis will be my energy term, y-axis will be my intensity term. One kind of intensity term will be there. Okay. Now question is that coming to the Mossbauer spectroscopy. Mossbauer is a defined spectroscopy where we are actually changing a nuclear state. Here in the UVs, we are changing the electronic state. In the UPR spectrum, we are actually changing the electronic spin change. In the NMR, we are actually changing the nuclear spin state change. Some difference, fundamental difference over there. See, first of all, we have to look into this. NMR, we are actually changing nuclear spin state change, nuclear magnetic state change, spin magnetic change. That is the, let's suppose in the higher proton, we have the plus half magnetic half in presence of the magnetic field, the magnetic, the I value of that is nuclear magnetic state changes to plus half to minus half, and in the AVR, in presence of the electron magnetic field, the electronic spin state actually changes to one is the plus half to minus half, or let's suppose half is the spin. Right now electronic configuration is that electronic spin is the half, only half, and then we have the plus half to minus half and plus half in presence of the magnetic field. In the UVBs, we are changing the electronic state. Electronic distribution actually changes into a somehow where my let's suppose my single state is there, and then we have the electronic state something like that where my first singlet excited state is there. That is, we are actually electronic state, actually electronic distribution actually changes into that molecules or anywhere. But in the Mossbauer spectroscopy, we have some nucleus into the nucleus. In the ground state, they have their own distribution inside there. Why? You are providing some external perturbation. Let's suppose we are providing in the nucleus external perturbation, that means we are providing some energy over there. And then we are exciting that nucleus to a different nucleus distribution. Let's suppose we have the nucleus distribution is initially ground state is a plus half, I equals to plus half, and then we are providing some energy into that distribution actually redistributed to 3/2. Initially we have the half, again we are distributing to 3/2, and that is the nuclear state we are actually changing. But in the NMR, what we are doing, we have plus half. We are not changing the plus half to plus 3/2. We have the nuclear state is the half, nuclear spin state is the half over there, and then we are applying a magnetic field into that state I, which a half is, which is actually two distributed at two different orientation. One is the downwards towards the my magnetic field applied, and upwards towards the parallel to the parallel to the my applied magnetic field, and opposite to the my applied magnetic field. Depending on that, we can say this is plus half and this is the minus half. Okay, so coming to that one, so we have some in the NMR. Let's suppose we start with the NMR. NMR, what is we are doing? What we are doing? We have the NMR spin. Let's suppose proton. We have, this is the energy we are talking about. Some S spin is the S equals to half. Now we are applying a magnetic field. Let's suppose this is the P0 we are talking about, and this spin state distributed into the, let's suppose this becomes the plus half. This will be the magnetic impedance of the magnetic field is mi becomes plus half, and then mi becomes minus half. Okay, and that is the transition we are talking about. This is not the nucleus actually transfer to here, but is the change of the state of that nucleus spin, nuclear spin. Now if we externally add h nu, which is actually this nu actually this wave is required for the radio wave, and depending on that we are actually getting the NMR spectra. Okay, now question is, if that is so, the all the proton has their same NMR spectra, but we are getting some different NMR spectra. Why this is so? So this is the nucleus we are talking about, but proton only have there, only for one proton is there. Proton, not the proton. We have, let's suppose hydrogen. We have one proton over there, so only we can get one NMR spectra, but we are getting different NMR for the different proton. Why this is so? So there is some electronic distribution. There is a one proton and one electron surrounding this my hydrogen atom. This electrons cloud, they have their own spins distributions. They are actually moving towards into that nucleus, and then they has their, while we are applying the some magnetic field, this electronic movement actually orients somewhere where they somehow they are opposing to my applied magnetic field, or surrounding or parallel to the my magnetic field. Depending on that, we can actually isolate how much electron density is actually present onto that particular hydrogen atom. They have their electronic distribution is different for the different proton, and then we can get a different NMR spectra for the different proton. Okay, let's suppose my one molecule we have, let's suppose methane, C, hydrogen OH. These three hydrogen are looks like similar. They are A and this is the B, but they are proton. They have one proton over there. This is the hydrogen. This is the hydrogen. The hydrogen A and hydrogen B, they must be coming into the same in the NMR, but the electron distribution around this proton and this hydrogen and this hydrogen is different. Here, this you can find this oxygen is a highly negative. Okay, electron deficient, highly negative electron deficient, electronegative element. It actually pulls the electron density from the proton, this hydrogen, and they reduce the electron density into that this hydrogen atom, and then we are getting only only less amount of electron density onto the proton, onto this hydrogen atom, and then they are actually opposing, or they are actually orienting towards the magnetic field with a less effect. That's why we are getting a different proton NMR with respect to this hydrogen one. This hydrogen we are talking about. They have a different, this one also have a different position because of their electron density of that particular proton is different. Okay. Now interestingly, we have some nucleons. Let's suppose we have the proton, we have the carbon, we have the fluoride, we have the phosphate, everything. They have their different magnetic moment, different I value, electronic magnetic moment. The proton, if proton actually have the, depending on their magnetic magnetic susceptibility, they are face a different magnetic moment, magnetic field, which is actually applied to the molecules. So depending on we have, let's suppose we have proton 13C, we have 19F, we have 31P. Most generally used these four NMR. Also people are right now using lithium. Also they are also tuning someone tuning mercury, lead, all those NMR, all those elements, and they have their different magnetic susceptibility. So for hydrogen, it has the highest magnetic susceptibility, which has a 2.7927, and we have 0.7022 for the carbon, 2.6273 for the fluoride, and my phosphate has magnetic susceptibility is at 1.1305. Don't need to remember all those things. If my proton field 500 megahertz of magnetic field, in that case, in that magnetic field, carbon will feel only 126 megahertz because of its magnetic susceptibility is 4 times less than my proton. Okay, and this fluoride also can feel 470 megahertz, and this phosphorus will feel 202 megahertz. As their magnetic susceptibility is different, they are different sensitive in that particular instrument. So that's why whenever we are recording the NMR spectra of the carbon, we need less amount of scan. Scan is less. We need here is a 4 times less sensitive. So then we need a very high number of scan. High scan needs. For the carbon, we need the high scan. Okay. And the phosphorus, and then we Phosphorus also has a, we don't need that much of scan. It's near about the proton. If you scan 20 or 50, then you will get the very good data for the fluoride. And the phosphorus we need a little bit higher scan, but lesser than the carbon. Okay. Now coming to the another spectroscopic technique where they use a different energy to calculate the rate is called electronic spin state change. That means we have our nuclear spin state, we have right now we have the electron spin state that is called EPR, ESR, electron spin resonance. Yes, sir. It's similar to the NMR. We have the electronic spin state. Let's suppose we have spin equals to half the energy we are talking about, and we have applying the magnetic field, that is the H we are talking, and we have is forming two energy state. If it will be that electrons is charged with negative, that will be my positive plus half, and that will be my minus half. Okay, sorry, minus half. This is mi, sorry, it's called ms spin. Ms equals to minus half. Okay, and then we have the energy gap over here, delta E, which is called G beta H. G beta H. And then, so whenever we are recording any EPR data, we have some intensity over here. We will get, we are actually talking about H over here, field. We are changing the field, and then we are getting some this kind of data. If you thinking it's observance scale, but in that case we are actually mainly a derivative of that observance one. That's how we are getting. We have the APS spectra like if you do the derivative of the this Gaussian curve, we will get definitely this maximize for this G, actually this G value for the free electrons is around 2.0023, and for the free electron that will be this G, for this G should be 2 point something 23 for free electron. Okay. Similarly, the IR and UVBs we are together. We will talk about together. We have some IR and UVBs spectra where we have my over here. This is the potential energy diagram we are talking about. This potential energy actually associated with some vibrational energy, and similarly this one also have some their own vibrational energy. This is V equals to 0, V equals to 1, 2, 3, 4, and dot, dot, dot. So the change between these two states, it is called vibrational state change. State change. And the state change from here to here, this is called electronic state change. This is happening in UPV's region, and this is happen in microwave region. And also EPR also this energy, the H nu, which is actually happening in a microwave region. Microwave region. Okay. So this is vibrational energy where we are doing the microwave region, and if you are also doing the microwave region, the electronic state change where happening, this is required the UV region. Now, Mossbauer is the one thing where we need the nuclear state change. So we need the nuclear state change. State change in the Mossbauer spectroscopy. That is happening as a gamma ray region. Okay, so depending on the energy, you can isolate all the spectroscopy, but my energy is less than 10 to the power minus 5 ev. We have NMR, need radio frequency. Okay, then we have the energy around 10 to the power minus 4 to 10 to the power minus 3. So microwave. That means EPR or ER. Then we have the optical spectra, which is NIR, become visible region, and we can say Fibis region. Then we have the X-ray diffraction. The energy region is around 10 to the power 3 to 10 to the power 4. So X-ray. And after that, the energy which is then 10 to the power 4 ev, which is actually gamma ray. Okay, this gamma ray actually requires gamma ray to change the nuclear state. Okay, so let's suppose we have some nuclear state. Let's suppose this is my energy. We have the pi equals to plus E equals to half. While we are putting into the magnetic field, we'll get minus half plus half. While we are putting into the B0, while we are providing the gamma ray, this I equals to half becomes the I equals to 3 by 2. Again, this 3 by 2 in presence of magnetic field, we can make plus 3 by 2. Oops. 3 by 2 half minus half and minus 3 by 2. This state change can be recorded by the NMR, but it's supposed to be this 3 by 2 supposed to be stable. This gamma ray actually change my nuclear state. This is the difference. One is the NMR is nuclear spin state change. Gamma ray is the Mossbauer spectra in the nuclear state change. Nuclear state change, distribution state. We have the some nucleons. Overall nucleons, we have the I value is around, that is the nuclear magnetic moment, which is around plus half, let's suppose. And while we are actually exciting by the gamma ray, this nucleons is distributed to some other I value, that is the maybe 3 by 2 or other value. First of all, it's supposed to be 3 by 2. And then we'll get the Mossbauer spectroscopy coming out of that phenomenon. So that will come into the later part of that your this lecture series. Okay, so nuclear state change may affect the electronics. Okay, now how we need the change the nuclear state? We don't need that. My question will be or always be there. How we need the nuclear spin state need to change? We have some other spectroscopic technique which can be used for my detection of the molecules. So why we need it? So can we detect something special which is actually not can be detected by the other system, other spectroscopic technique? Yes, we have some. So that's why Mossbauer spectroscopy comes into the picture. As we know, we have some nucleus over here. We have electrons over here. Electrons, nucleus. So as this nucleus has some effect onto the electronic field, if we change the nuclear state, that also affect the electronic field that we found into the EPS spectra. Let's suppose we are looking into the nuclear electronic spin state change, electronic spin in the EPS spectroscope. If we have the different I value for that particular system, let's suppose we have the one electron unpair one electron. It suppose have one peak for the particular unpaired electron. Let's suppose we have another example for the copper. Copper has a I value is 3 by 2. And if you record the EPS spectra, you will get the 5 spectra. Because of the copper has a some effect of 3 by, it has a 3 by 2 I value. So I by 2 is give me the 4 signal, 2 Ni plus 1. But we are getting 5 signal. Why? We have directionality asymmetricity into the cover. So that's why we are getting the 5 signal. But why this I actually comes into that? That is because of the hyperfine interaction of nucleus into the electrons, hyperfine interaction between the nucleus and electrons. That's why my spin state of the electrons actually influenced by the nucleus. Similarly, the electron has some interaction between the interaction with the nucleus. If we change the nuclear state, if my electron distribution is different, they will face some different energy state, but that is a very weak. So in the Mossbauer spectra, we need a very sensitive. It's this data will come the electronic distribution, amount of distribution, electronic spin state. That data is very minimal. So my signal to noise ratio will be very high. Otherwise, we cannot get it near to the noise level. We'll get the data. So instruments would be very sensitive. Otherwise, you will not get the data. And that is phenomena actually depends on the hyperfine interaction between the nucleus and electrons. So for the Mossbauer spectra, we can, by using the gamma ray, we can detect the, what we can get, the oxidation of that particular atoms. We can get the state of the system. Okay, and here is the all those data actually depending on the hyperfine interaction nucleus and the electron. Okay, and right now we are changing the nuclear spin state. Nucleus, not the nuclear spin state, nuclear state. We need the high energy. Why we need the high energy? Because all the nucleons closely packed together because of the binding energy. It's a huge binding energy. If you redistribute their orientation, we need a huge energy then. So that's why we need a higher energy gamma ray. So higher energy wave. So that's why we require gamma. Oh, sorry, lambda. We need gamma ray to redistribute the nuclear state. Okay. Now in UVs, we are getting the sodium lamp, deuterium lamp, or halogen lamp to get our light. But how can I get the gamma ray? Now question will be in our mind. Says what will be the source of the gamma ray? The question will be what will be the source? It's supposed to be exactly match where my sample actually getting absorbed this gamma ray. Okay. So then if our sample spins and nuclear state is changing to plus half, sorry, from half to 3 by 2, then my source should be half to 3 by 2. This is the decay, emit the light, and this will be my sample. It's the decay, absorb. Okay, and this is my source. So it's not a very easy process. We need some different, we need a source where the spin state actually changes to plus half to, from 3 by 2, the spin state 3 by 2 to become the half, and that generates the gamma ray, which gamma ray actually absorbed by the sample, and it changes its nuclear state plus half to 3 by 2, and then we'll get the Mossbauer spectra depending on their electron density. Okay, so this is the fundamental things we need to follow it up in the next upcoming session. I will try to make some problem and we'll ask some problem from there. Uh, we'll get some assignment also there depending on their problem. Okay, if you get any have any problems that, just let me know. I'll try to discuss it. So first of all, today's session we actually discuss about some, what is that? Some CD spectra application, and then we found some interesting result. For the this CD spectra actually found can help to say my system is aggregation, say my system is aggregating or not. And then we followed up how induction, how aggregations can make another kind of chirality, and then it becomes the CD active into that particular absorption region, in particular wavelength region. Then how we can say there is some induced chirality into the plasmonic gold nanoparticles, by the peptides one we actually covered it. And then there is some um, enhancement of the CD activity while we are exposing the peptides into that nanoparticles for a long period of time, because of they are making some different helical structure. And then we have moved towards the different spectroscopy that is called Mossbauer spectroscopy. Then we discuss about some little bit about what is the spectroscopy called, why it is mass is called mass spectrometry, why the UV is IR Raman are spectroscopy, mass is not the spectroscopy. Now we talk about the NMR spectroscopy a little bit, why why the radioactive sorry, why the radio wave is used for the transition, and why the different proton has a different NMR value, NMR shift value. So we discuss about that. Then we come into the APR. Why in the APR we need microwave in the vibration distribution, that is IR. We need the also need the microwave. The electronic state chain we need the UV region light, and depending on the energy state we divided some spectroscopy for the X-ray use around after 10 to 3 to 10 to 4 electron volt energies energies waves, and the gamma ray is required for the Mossbauer spectroscopy. So to Mossbauer spectroscopy we need the gamma ray. What will be the source of the gamma ray? So gamma ray source would be exactly similar where my sample actually getting absorbed, sample absorbing that gamma ray. So to find that, we'll come into the later part of the my discussion session. If you have a problem solving session, next we'll come into the next week. Thank you, guys. If you have any doubts, just let me know, by anyhow delay from the maybe that may be from attending the class, or that may be from comment of the my previous classes or any classes in the YouTube channel. Then we'll try to find out to solve that problem. Okay. To that we'll stop over here, and we'll come into the next session. Okay. Bye bye to everyone. I'll stop the recording.